So here's what we're going to talk about. So I'm proposing to go through the entire history of mathematics in this one talk. You know how it is. It's really difficult to know what to put in your talk. So I couldn't decide. So let's put everything in. But the story starts a long time ago. When I say at the dawn of humanity, it will sound like an overrated cliche, but it's actually true in this case. We're going to talk about something called geometria, which I'm sure you know is geometry. So this is what we have from the ancient Greeks. But in fact, it's important to remember that we have no record of humanity not knowing some geometry. So this is cool. It seems that people have been wondering about the world around them for as long as they could think. You see, so that's the most remote documents or artifacts that we can find indicate that humanity has been aware of geometry. And geometry, that's, as you also know, is a Greek word that's a conglomerate of two words, geo, the earth, and metria, to measure. That's what it is. And it's debatable. I think we can stretch the meaning of the word and substitute for the earth the whole world. Because, again, to the Greeks, astronomy was as much as a part of everyday life as trying to figure out how to erect statues and temples so that they don't fall over. It's an important practical problem. If you are charged with, just imagine that you're at the Acropolis and somebody is waving, okay, here's a rock, build me a temple on top of that. And you have no examples of anyone who's done something like that before. You see, you can't look it up on Wikipedia, how to build a temple of Athena on Acropolis rock. You know, that's you have to think. And so here's just a very short list of problems that people faced every day. Astronomy, very closely related to navigation. Surveying, whenever you wanted to build anything or measure the land that you have grabbed or measure, this is important to know how to do it. The Greeks, I actually bought a wonderful little book, The Inventions of the Ancient Greeks, which is just so much fun. And here's a picture of one page from that book. It's remarkable to see how inventive the Greeks were when it came to constructing and building sundials. You know, just to us, a sundial is just a garden ornament that plays no practical role. But again, if you want to know the time, you have to build something that will tell you the time. And of course, it's an easy observation to make. It's enough to be on this planet for one day to know the shadows move. You may not know why, but it's clear that the shadows move. You need a little more time on the planet to know that they move periodically. You see, that's a different discussion. So here's an example. You know, it's some kind of arrangement which is essentially a sphere hollowed out from a block with a little hole on top, and the sun comes in, and it's marked in a variety of ways, so you know the time and so on. Pythagoras. I don't really think Pythagoras looked like this, because I don't think we know what Pythagoras looked like. So I bought this is a fridge magnet. I bought it in a souvenir shop in Athens, and the young person who sold it to me said, he made my life very difficult in school. So I'm sure that, again, this is a sentiment that we can all relate to. It's been handed down from generation to generation ever since Pythagoras. I started with Pythagoras, and I apologize for insulting your intelligence, but there is actually an interesting reason why we want to talk about this. In fact, several reasons. So this is what Euclid reports as Pythagoras' theorem. So allow me to read it out loud. In a right-angled triangle, the square on the side opposite to the right angle equals the sum of the squares containing the right angle. Boring, huh? You know this. Notice that there is, when we talk about squares, there is no mention of area. It just says the square on the side opposite equals the sum of the squares containing the right angle. There is no mention of area. For one important reason. For the ancient Greeks, geometry was used to represent arithmetic operations. There was no notation for arithmetic operations. Also, numbers did not have an abstract existence, as far as I can see, the way they do for us. When we say 7, that somehow makes sense independently of any geometric interpretation. In the beginning, when you said 7, you really meant 7 units of something, right? So numbers were to be represented by segments of an appropriate length. To multiply numbers meant to construct a shape whose area was the product of the two. So the square is the square of some number. All right. So this is a modern interpretation that you will see shortly, that you know very well. Rephrases this, but for them, you really, if you wanted to prove Pythagoras' theorem, you had to show that that square equals the sum of these two squares. Right. So all of a sudden, this looks like something to do. Okay. And of course, they were incredibly adept at creating all kinds of wonderful geometric things. So here's a very short instance of Pythagoras' theorem where you can see it in a tiling, and here you can prove it by just counting the number of tiles. So the isosceles right triangles are very easy when you want to prove the Pythagoras' theorem. Just build yourself a tiling and count. Okay? So, of course, we might quibble if that's precise enough. I can't resist showing you something that you probably know very well. Here's a proof attributed to Einstein, or was probably discovered by a number of people. So here's what you do. You want to show that the area of these, so you want to relate the sum of the areas of the two triangles to something that you construct on the, you know what you need to do. I need to explain, I don't need to explain Pythagoras' theorem to you. But here's what you do. So let's see, is this going to work? Hello? Okay, sorry. It's a little slower than I thought. I haven't used my iPad for this. No, okay. Okay, so this is what we are trying to do. We have 3 triangles that we made from the original one, which is indicated in blue here. Okay, we have constructed the 3 squares on this. And now, you see, here's Einstein's insight. This is the beautiful simplicity of thought. You had no idea a priori how to relate the surface area of the square to the surface area of the triangle on whose hypotenuse it's built. But it doesn't matter. You can convince yourself through geometry that was known to Euclid and Pythagoras that these are similar triangles. Okay, so no matter what ratio this is, it has to be the same for all 3 triangles, because they all look the same. So the insight is that the area of the triangle divided by the area of the square has to be the same for all 3 situations. Okay, there is no reason why they should be different. Okay, all you do is you scale. Okay, so this is not great. You just don't care that you don't know. Let's see if but in modern notation, if that constant is f, it means that some constant times the square of the side plus the same constant, and so on. So this is the equation that you immediately recognize as Pythagoras' theorem, and this is Einstein's proof. That's it. This is you just look at the geometry of the situation, and it reveals what should happen. I may have mentioned this to you in lectures, but it merits repetition. The fact that we can write Pythagoras' theorem in this form is a huge advance, and it took humanity probably 1,000 years to invent notation to write Euclid's statement in this form. And it's done two things. First of all, we can be precise about the statements that we are making. Interpreting verbal descriptions of statements is never easy. This is unambiguous. But also we can compute with this. Okay, so this is much easier than what Archimedes had to do. Let me take a detour into even history that was ancient when Pythagoras was alive. You see? So the Babylonians, so this is a clay tablet from 1800 BC. So that's like 15 centuries before Pythagoras. And there people have uncovered that they knew Pythagorean triples. Okay? Not only that, these are gigantic numbers. This is not something you can discover just doodling. Okay? If you thought that you could find that, here is something even more gigantic. We don't quite know why they wanted this, other than this is a neat way of keeping track of computations. As you know, computing squares of numbers is laborious if you want to do it by hand. So if you try to calculate, for example, one application would be trying to calculate the square of 8,161. If you happen to know there's the sum of two smaller squares, maybe you can just look them up in the table and just add them instead of multiplying. So here's the Babylonians, and here's what I meant when I said, Babylonians is like prehistory. It's on the verge of the existence of solid artifacts. And there's a very solid trace of Pythagoras' theorem right there. Archimedes. This was one of the brightest people who ever lived, I think. And he's made such huge contributions to what we now know as mathematics that it's incredible. Here's something that he's done which survived to this day. As you know, he preoccupied himself with invented numerical procedures for measuring the area of shapes. And here's one of his main discoveries. The area of any circle is equal to a right-angled triangle in which one of the sides above the right angle is equal to the radius and the other to the circumference of the circle. So you see, again, there is no mention of area. He says this object is equal to this object. But again, the reason for doing it this way is that, okay, assuming that you can measure the radius and the circumference, especially measuring the circumference is not easy. This gives you a way of actually computing the area, because computing the area of the triangle is something very, very easy. And in modern notation, it goes like this. Okay, so this is the area that you calculate, and so on. So this is the formula that's. But this is another result that he found, which is incredible. The ratio of the circumference of any circle to its diameter is less than 3 and 1/7, but greater than 3 and 10/71. So again, in modern notation, when you work out what these things mean, this gives you an approximation of pi that puts it between these two numbers, and the higher of them is 22/7, which is a popular rational approximation of pi. Okay? That gives pi to 2 decimal points, if I remember correctly, calculators, and gives us the excuse to celebrate the Pi Day on the 22nd of July. So that's when we celebrate the Pi Day in this country. In America, you can celebrate this on March 14, which is 3/14 in their convention, which just happens to be Einstein's birthday, which is a very appropriate way to celebrate the Pi Day, and you normally celebrate it by eating pie, which is, what else would you do?
You celebrate my birthday.
That's what you do. But let's, just to introduce ideas that we will use later, let's just you know this very well, but let's be astonished again by Archimedes' ingenuity in estimating pi. So he figured, okay, I want to calculate the area of the circle, and I can't do it. But he knew how to compute areas of simple shapes, like triangles. That was known to every child in Athens in his time. Well, no, not every child, but a few children. So you know how it is. You find a shape that you know. For instance, two hexagons, you inscribe one and circumscribe the other one. Okay? So the inscribed hexagon consists of 6 equilateral triangles, and the circumference, so we have calculated the circumference. So the circumference of the inscribed hexagon is 6 times the radius of the circle. Okay? And the circumference of the circumscribed hexagon, again, Pythagoras' theorem that we just reviewed will tell you that that's what it is. The circumference of the circumscribed hexagon is 4 times square root of 3 times r. So this is our achievement. We know that pi is between 3, it's greater than 3, and smaller than about 3.5. So he beats us like by a huge margin, right? So, and in fact, he figured out how to push this idea by bisecting. So if you have a hexagon, you can bisect each side to create a 12-gon, and then do it again and do it again. And he knew how to carry one estimate over to the next stage in this iteration. So to do this with this accuracy, he needed to consider a 96 gon. This is not something you can draw. When you plot it with modern computer tools, it looks like a circle. A 96 gon cannot be distinguished from a circle, right? So he had to do it drawing figures with his finger in the sand. That's not apocryphal. That's how he did a lot of his mathematics. And as you know, he got killed trying to solve one of his problems. Oh, sorry, he didn't get killed trying to solve. He was killed while he was solving one of the problems. And the story, as I'm sure you know, is that he got killed by a soldier who was sent to protect him in the Battle of Syracuse. And the soldier couldn't really be patient enough to wait for the old man, so he just killed him. So that's a shame. But that's humanity. That's what it is. So let's just take a few steps through another important part of measuring the world, which is mapping. This is how we know how our world looks. We try to put together all the local information that we have gleaned through our lives and paint some global picture of the world. So here's a map from about 300 BC. As you can see, it's terribly out of shape. It's got lots of missing bits. The seas are tiny, the land is huge, and there are many problems with this. Measuring anything on this scale was difficult, and it's still difficult to this day. That's one. Second, people didn't have any fixed units of length. Until very recently, and I really mean a few centuries since we started navigating, there were different ways of measuring distance on land and different ways of measuring distance on sea. On land, you walked, you rode a camel, you rode the caravan or something. On sea, you rode, well, your slaves rode, right? Or you sailed or something. So these were two totally different modes of transport, and it wasn't easy to translate the distance traveled by a galleon in a day across the sea where you can't walk to a distance traveled by the caravan in a day. So that's part of the reason. It may also explain the difference in distances on land against the sea. Perhaps it's quicker to sail than to walk. See, so it's somehow distances when you walk are longer than when you sail. So this is state of the art map in 1150. You had to be a king to own the map like that, and was made for a king, and I forget which one. So again, I mean, this looks a little more like Europe, but things are out of proportion and out of place. We had clearly no idea of how the land pieces fitted together. Okay, so I'm sure that people knew a lot of things locally very well. They could clearly travel long distances. Marco Polo went to China and back, and he wasn't the first one to do it. Genghis Khan sent his troops all the way from Mongolia to Europe. So people knew how to do it. The Vikings, as you know, sailed to North America in the first millennium. So, but actually putting it on the map was tricky. So this is the age of discovery. 1553, this is when Magellan sailed around the world. That's more or less the time of his journey. You know, the first guy to circumnavigate the world. He had this obsession that there has to be a passage through South America, which he found after a huge amount of effort. And there is something called the Magellan Strait, which is just above Tierra del Fuego in South America, which is where you go to Antarctica from, which I would like to do very much. So, has anyone here been to Antarctica? We should go. We should organize a student mathematical trip to Antarctica. We can invent some reason. Like, we want to count the penguin. It sounds mathematical. Mathematicians count, so let's go count the penguins. Anyway, but look, there is no western edge of this continent. So he sailed, he was proposing, in fact, he sailed around the world using a map of this accuracy. There was nothing more accurate. People relied on something called logs. So navigators kept notes, saying essentially things like, so I sailed in this direction for so long, and I had a wind which was from this to there, and roughly so strong, and so on. So as you know, the logbook, you know how people measured velocity of a sea voyage. You know that, or you don't? No. That's exactly right. So you had a log, which is a piece of wood with a rope tied to it with knots at regular intervals, and you chucked it overboard, and you just paid out the rope, counting the number of knots in a given unit of time. Measuring time at sea, of course, was a separate problem. And part of the reason is that we had, as I said, no established units and no established system of coordinates, and that took a long time to figure out. And as you well know, there was this guy, René Descartes, who in the 16th century came up with the scourge of every school child ever since. Right? That you have to learn those stupid coordinates, remember which way x goes or which way y goes. Why did it go this way? Why does x go to the right and not to the left? Why does y go up and not down? Why is it always like this and not sideways? I mean, sheesh. We have to learn this stuff. But you know that, in fact, this is Pythagoras' re-emergence, of course. But now it has a different meaning. Now you know that if you introduce coordinates, you can measure distances. So Pythagoras' theorem allows you to translate easy measurements of length, which was known to ancient Greeks. I told you that numbers to the Greeks just meant numbers of units along the lines. The Greeks were happy with this, and the Greeks would be happy with this. And Pythagoras gave them a way of calculating distances across their units, but it was only after Descartes' discovery that this was really feasible as a computational device. Something else happened. This looks like a trivial observation, and you know this very well, but this is when we can put geometry into algebra. Instead of talking about geometric shapes like Archimedes had to do, we can talk about equations. And that's great, that's a huge progress, because we can manipulate these equations far more easily than we can manipulate these figures. And this leads to huge progress. So now you can have shapes which look crazy compared to what the Greeks could do. And we can plot them so you have beautiful, beautiful pictures that you can do. And all the way to the modern age, this is really what we want to know about. If you are creating an animated computer-generated movie, your computer needs to know an awful lot of computational geometry. This is where it lives. So every time you see a beautifully rendered animated film made on a computer, there is an entire human knowledge of geometry that's there. And I really mean it. It's really tremendously sophisticated computational understanding of geometry. So from Pythagoras to animated movies, there is an uninterrupted line through geometry. And so if you hate Pythagoras, just think of your favorite animated movie. So let's have a vote. What is your favorite animated movie of recent years? People are afraid to warm up. You see, one advantage of getting old is that you acquire children. And once you have those, you can go and see movies and pretend it's their fault. It's tremendously useful. So I may have seen more movies than you. So Up is my favorite. Up is my favorite all-time movie. But you see, so in order to render anything as complex as the Earth or as the face of an old man for a computer-generated movie, again, you need to use this idea that was invented by Archimedes. If you want to understand a complex shape, try to understand it through a collection of simpler shapes. See how they fit together and see what information that you get. So this is something which is, again, very practical and tremendously important. How do you measure the area of a country? Okay? How do you do this? So we can measure easily areas of small things that we can hold in our hand, but something as big as a country or the whole planet or a continent. So this is Archimedes' idea, which was developed into triangulation. And that is, okay, you divide your country into simple shapes, triangles, for instance, and you do it precisely enough so that you can calculate the area of each. So typically what happens is that you set out one such length, call it the base, measure this length very, very accurately as you can. Then start constructing triangles that you can see. So you do this by erecting markers that you can see across long distances. And I really mean long distances, tens or 20s of kilometers. Okay, the longer the better. Have fun with All right, and then you have this tremendously complicated calculation where you compute the area of each triangle separately and add it all up. So I mentioned this because people dispute the divisions between pure and applied mathematics and so on. So here's another name. The great Carl Friedrich Gauss, one of the greatest truly pure mathematicians that ever lived. I think he's the guy who actually invented pure mathematics in the sense of creating a body of knowledge through logical thought. He was the main contributor. He was tasked with supervising the surveying, the triangulation of northern Germany. He was a professor of astronomy at Göttingen, and he relied throughout his career on the generosity of the local prince. So when the prince asked him to measure how much land he had, Gauss couldn't say no. And he actually, he did this to the point where he traveled on horseback and on foot, talking to people, talking to farmers, because fields were trampled and so on, trying to arrange this. So for instance, he measured that the distance from Hamburg to this small village of Wielstede is 42,454 meters. So again, at this stage, we had precise units of measurement. But this is definitely something that Archimedes would recognize. He may have been amazed by the accuracy of the measurement and the computational techniques that have been devised since his time, Like you could say, yeah, great, yeah, that's how you do it. And now we get to data. And in fact, data sounds boring, so it's big data. So there's a bit of a jump, but the connection is this. We are passing here from very physically observable problems of measuring something geometrically to something which may seem a little more esoteric in the sense that data exists in a slightly different way to, say, planets or countries or tabletops. But I will show you that the same ideas actually apply. There is a huge, there are interesting parallels. So first, what is data? So until recently, data were numbers typed on a piece of paper, like this. This predates Excel spreadsheet. There was a time, you may or may not know, when the Excel spreadsheet did not exist. Archimedes, for instance, had no access to Microsoft Office. But then data is many other things. It's definitely shapes. So for instance, here is something which is quite exciting. It's these are pictures obtained from X-ray molecules. We can X-ray molecules. We can create X-rays of single molecules. And this, in fact, is something. It's a technique known as the cryo-electron microscopy, which is really neat. To create this, you take a one molecule thick or thin, I should say, layer of your compound, cool it down until they stop shaking, and X-ray this, and this is what you get. There's more shapes. Imagine that you want to trace evolutionary paths of animals. How would you do this? Well, you can take some characteristic bones, teeth in this case, and this is lemurs and related species, and you try to trace how this shape changes. Again, so your data might be a collection of these objects with perhaps some points marked, and your job would be to compare them, see how they differ or are similar. Continuing with evolution, this is the kind of data that you get out of genomics. Okay, so there are some genes here, and there is some expression data here. There is an awful lot of research into genetic foundations of various diseases, cancer, for example. And there is now a very recent study, this is like last year, where people have discovered that cancer cells actually evolve as if there were species. That's part of the problem in fighting cancer. That you get a cell, and we know it's a mutation, but then it evolves, so it can split into subtypes. And this is your data. This is what you manipulate. So this is something that we do here, and I showed this picture to a number of you. But you know, this is a representation of CT scans of human lungs. This is when you exhale, and this is when you inhale. How do you compare objects like this? How do you classify them? So topology is something that will help you to do this. And topology begins with an idea which, again, would be familiar to Archimedes. Approximate complex shapes through simple ones. Okay? So if you have a sphere, mark some points on it. And instead of having this round shape, take something which is made of triangles, which approximates this. So you put vertices where you put vertices where you have selected points, connect them with edges and so on. At this stage, Archimedes would object, because he would say the object on the left looks nothing like the object on the right, and that's clearly true. Okay, and this is where topology. This is this breakthrough idea that perhaps it is sufficient to create an approximation of your object which is consistent with some notion of continuity. It's clear that if you imagine that you blow into one of those vertices, you could inflate that to become this. That's clear that you could do this, right? So So there is a continuous deformation of this object that would give you this. Equally, if you were to deflate the sphere, keeping the vertices where they are, you would get this. And in fact, we know this from every day. So this is the difference between geometry and topology. Geometry can see a distinction. You can see a very distinct difference between this shape and this shape. Topology says they are equivalent in some sense. I can continuously deform this to become that, and conversely. In real life, Archimedes would say, oh, so try kicking this. It's not a very pleasant thing to do, whereas people do kick these shapes routinely, it seems. And so it is. There is another, once you move beyond the rigidity imposed on you by geometry, so geometry is very particular about distances, and this is why this is convenient for mapping anything. If you move beyond that, you can play with the following. So here's a picture. I'm sure you know the Königsberg, 7 bridges of Königsberg puzzle, but let me take you very quickly through it because it's interesting. So the puzzle is like this. In the city of Königsberg, which is now called Kaliningrad, there used to be this arrangement of bridges and land masses. And if you go for a walk, it was a question, does there exist a path that traverses every bridge exactly once? So this is 18th century. And another great mathematician called Euler invented the following approach to this. He says, if you're really interested in bridges, then the shape of land masses makes no difference. It contains no information. So let's just count how many distinct land masses you have. So these are the vertices of your graph. This corresponds to this bit. The one in the middle is this island that you can see. The one at the top is that thing there. And the one on the right is what you have between these two rivers. And then they are connected by a number of bridges. So let's make an edge here for every bridge that you have. Okay? So now any walk is a path on this graph. So what does it mean to go for a walk? Well, you start somewhere. Okay, so you leave that point, and then you have to pass through bridges. So it means you do not. So right. So what I'm trying to say, every walk will have one beginning and one end. How is beginning and end different from every other piece of the graph? Where you start, you leave, and then even if you come back to it, you have to leave again, because that's not necessarily the end of this. So the start would be characterized by having 3 legs attached to it, and the end similarly. Everything else has to have the same number of entrances as exits. So this is how you solve this puzzle. You see how many beginning and end points do you have, and how many do you need to have. Okay? So Euler said, for this to be possible, there has to exist at least, the diagram has to be such that you have at most one start point and at most one end point. Every other point has to be a transit point. So you can have at most 2 vertices with an odd number of legs attached to them. All the other vertices have to have even numbers of legs attached to them, because they are not the beginning and they are not the end, so you have to pass through. So if you come, you have to leave. If you come, you have to leave. If you look at this diagram, you can see that this is degree 3, degree 3, degree 5, degree 3. So this is not possible. So this is the kind of example that simplifies thinking. So let me quickly tell you about modern techniques that arise from this simplification of shapes by approximating them by something else. So this is something that, it's a technique called mapper, but it's known from how you depict 3-dimensional shapes on a two-dimensional map. So you have a shape you want to describe, so you give yourself a height, a direction. This can be done in many ways. So split this region on the left into some characteristic regions, sub-regions according to the height. But by characteristic or interesting, we will mean regions where some structure changes. Okay, but keep the information of what is attached to what. When you do this, oops, sorry. When you do this, you can then translate this shape into this collection of blobs. This unit goes to this blob, those two yellow bits get those two blobs, and so on. And you keep the information about how they intersect, and it gives you this very crude approximation of what you have on the left. What's interesting is that the one key property of this shape on the left is that it has this hole in the middle, which we can still see. And it also has those two flares, which we can also see. And let me show you something. So the data that I showed you at the beginning comes from a study from 1977 of diabetes, where you had 144 patients, 5 variables for each patient. That's the table that I showed you. And the data, so it's just 145 points in 5-dimensional space. And they say that's in one description, the data set was examined with a Prim9 program at the Stanford Linear Accelerator Computation Center. We don't know what that is, but you can bet that the Stanford Linear Accelerator Center had the state-of-the-art computation facilities. It's like CERN is now back then. Okay? Sorry?
You probably had a calculator at that point.
Yeah. But you see, this is the abstract from this technical report from Stanford University in 1977. So again, this is state of the art. So they described the procedure that allowed them to plot this. So there was a procedure, and there was one sentence here. When this was done, the picture was that of a boomerang with 2 wings and a fat middle. That's a technical report from Stanford University. And this is what it is. Here's a boomerang with 2 wings and a fat middle. So this is an artist's impression. You see, they reduced down from 5 dimensions to 3 dimensions, and then a human had to figure out how that looked. So these days, this could be done on a mobile phone when you are ordering a pizza. And this is actually true. The mobile phone could do this calculation. They are quite powerful computers with their phones. But you see, this boomerang with 2 wings in the fat middle has the following relevance. The fat middle turns out to contain people with control. So this is a study of diabetes, which trying to distinguish diabetes type 1 from diabetes type 2. In particular, the question was, can you have both type 1 and type 2? So the fat middle were people with controls, so people with no diabetes. And when you remove that, you set falls into 2 disconnected pieces, one wing and the other, and one of those is diabetes type 1 and the other is diabetes type 2. So this very crude, very topological approximation of your data, this is a picture we created with using the mapper techniques. The fat middle is this, and this stick person has 2 arms, but the relation is the same. And this is a very recent result from 2015, where this mapper technique was pushed to understand that there are actually 3 subtypes of diabetes type 2. And that's crucial, you see, because these various subtypes may or may not respond to a particular treatment. So it's crucial to know that. Let's just show you something a little more exciting. So this is, well, all of this is exciting, but this is something a little light-hearted. So this is something, this is data we got from the Zooniverse project, which is citizen science consortium, where people collaborate to analyze, for instance, pictures of distant stars, hoping to classify galaxies. So attached to each project, there is a forum where people say things like very pretty, or overexposed #star, or Hubble stars awesome, you know? And yet, important discoveries were made through this. So, if you want to make sense, and this is what we did recently, you can use a very modern extension of this mapper technique to create a picture of this complicated data set according to what people are saying. You can see how they collaborate, or you can see what words they are using. So this is what these two different diagrams show. And this is essentially all I want to say here. You see, I hope that, I'm sure you know this, but this essential unity of mathematics is something which is just so wonderful. It's not really accessible in any other area of human activity. The fact that Pythagoras' theorem has not gone out of fashion, hasn't been ridiculed on Twitter, still has friends and followers. That's difficult. I mean, if you maintain this kind of presence for millennia, well, you see. Also, mathematics, as you know, people typically think that mathematicians count. We do count. But what's more important is that mathematics is simply a systematic way of thinking about difficult problems. That's all it is. You see, if you have a complex problem, you need to somehow relate it to what went before. And then after you've solved it, you need to write down your solution in a way that will be comprehensible to people who come after you. You see, this is why we insist that you learn the language, that you learn the structure, and so on. This is why. Okay? Other than that, it's just a way of thinking about complex problems. So it's not some magic that you need to invoke. No, if you think about the complex problem, you are doing mathematics if you do it in this particular way. But this is the human bit. Truth and beauty. This is something that has always excited people, and we can see the excitement in Archimedes' writings that survived, in Euclid's books, and so on. We can relate to this. These were the people who tried to solve problems because they thought they were cool. Okay? Archimedes did not really have to invent a way of constructing an anti-six gon. For practical purposes at his time, our own crude approximation of the value of pi would probably be sufficient. Okay? Even if we could compute things more precisely than he could, people couldn't build them. So we find numerous examples everywhere. Like, why did the Babylonians bother to compute those huge Pythagorean triples? The most obvious hypothesis is that it was fun to do. Right? You could show off. Look, Mom, I found this. I mean, that's what it is, I think. And mathematics never forgets. That's another thing. This is why we still have it. You see, that's again the main reason why we do things in this particular way. It's so that we contribute to something that's far bigger than any of us, and it's our common thing. It belongs to all of us somehow. We all contribute to it. It's again, I think it's good to be amazed by this. It's good to be amazed by this. It's somehow, mathematics is not a collection of stupid, boring facts that we force you to memorize. It's far bigger than this. Right? The stupid, boring facts are there so that you can understand what it's trying to tell you. But this is all. Okay, so I think it's a good place to start. I'll run over time. But yeah, okay, thank you.